Hello everybody. So welcome to this week 8's lectures on linear systems theory. So this lecture will be a very brief introduction to the concept of observability and constructability. So let's start with a motivation of why we need to define the concept of observability. So a quick recall of what happened in the previous week's lectures. So we were talking about LTI systems. We were talking about their controllability verification. We were talking of stabilizability and so on. And towards the end, we had a notion that if the pair AB is stabilizable, then there exists a feedback control law of the form U equal to minus Kx that stabilizes the system 1 for which A minus Pk is a stability matrix. Okay. Now, the point is, okay, how do we get this X? So, what do we have for measurements is the following. So, I measure the outputs. These are what are available for measurement. So, assume that if C is invertible, then I can determine this X instantaneously and can directly feedback, right. So, this U can be directly computed as U of t is minus k times X of t, and the feedback control law, the implementation of that is kind of trivial. It's very straightforward. However, what happens is if the number of outputs are strictly less than the number of states, then the output matrix C is not invertible, and hence X cannot be instantaneously reconstructed. So, an interesting question to be asked is if only the output Y can be measured when the number of outputs is strictly smaller than the states, will it be possible to implement a control law which is U equal to minus Kx? Okay, I do not know the answer at the moment, right. I would like to say, oh well, let me construct a system where C is invertible, but it is not always possible to measure all the states of the system because of physical constraints and so on. Okay, so how does an example look like? So, I have an electric network which looks something like this, where I have an input U, output is a voltage measured across here. So, is it possible to develop a controller for the system where the control law is where I want to control x1 to some voltage, x2 to some voltage, and I just have one output for measurement. So, with this one measurement, can I control x1 and x2 or even stabilize x1 and x2 independently? So, that is what we will try to answer. How with the measurement of outputs can I reconstruct the state? Okay, so this leads us to define what are called as unobservable and unconstructable subspaces. So, how does the definition go? Okay, so when the number of outputs is strictly smaller than the number of states, we cannot instantaneously reconstruct the state from the input and the output, right. So, that is what does it mean by instantaneous reconstruction? Can I always do this when C is not invertible? Well, the answer is no. Okay. Now, I ask a different question. Would it be possible to reconstruct the state given some measurements over t0 t1? I know U between t0 t1, I also know Y of t over this interval. Okay. So, based on this information that I have, I characterize two notions here of state estimation, and because I really want to know what the x's are, and these are the notions of observability and constructability. So, observability refers to determining x t0 from the future inputs ut and yt, right. So, I know all these measurements ut between t0 and t1, I know yt between t0 and t1, can I actually construct x of t0. Okay. So, conversely or a little differently, constructability refers to can I determine xt1 knowing the past inputs, right. If I know all inputs from t0 to t1, can I actually determine what is the state at the time t1. Okay. So, these are the questions that we will try to address, not really address, but at least define problems related to how to formulate this based on the information that I have so far. Okay, so the first thing is okay. Let's start with a continuous time LTV system with equations of this form. The output. Okay, so we spend a lot of time on how to compute the solutions of x given these equations, right, from the state transition matrix and so on. So I just substitute the value of x here and I get the following, that the output on the interval t0 to t1 can be expressed well based by the solutions in this form. So y of t is c with the state transition matrix, the initial conditions and this terms in the integral, and of course dt plus ut. Okay, I'll not go into the details of this. This was done extensively in lectures on week 4. Okay, so observability of this system indicates determining the initial states x naught from the output equation, right. So this is the output equation. Sorry. So this was the output equation, and I want to see if I can determine x naught from the output conditions. That is, okay. So I want to determine x naught having known this y tilde here. Okay. So okay, I just so y tilde is just so I call this as y tilde, and then this just turns out to be yt minus this entire term here. Okay. Now, so can I solve this problem? Okay. So what is the definition? So given two times t1 and t0, the unobservable subspace, right, I denoted by u of this O t0 t1 consists of all the states x naught in Rn for which c phi x naught equal to 0. Okay, so this the I don't really talk of what is x0 at the moment. I just I'm looking for solutions of this equation, right, coming from here. Okay. Now a system is observable if its unobservable subspace contains only the 0 vector, right, which means the unobservable space, right, which is all the states. So x0 contains only the 0 vector. Okay, so some nice properties here. So if I have an input output pair ut yt, right, for all t0 in t1, when a particular state is compatible with the input output pair, then every initial state of the form is also compatible with the input output pair. So this is also compatible. Okay, so why is this true? Let's say that if xu is in the unobservable space t0 to t1, which means that c phi of t0 xu is necessarily equal to 0. Okay, and then what is with the other input with x naught? So there will be some y such that this y of t is c of t. This will also be a function of t here. C of t phi t t0 x naught. Then if I add these two, what will I have is that y of t is equal to c of t phi t comma t0, right, and then what do I have here is x naught plus xu. This is for all t in t0 t1. So this is also compatible, right, this and this via this c and phi. Okay. Okay, then the next step. So when the unobservable subspace consists only the 0 vector, then there exists at most one initial state which is compatible with the input output pair. Now this will be important for us, right. So when the unobservable subspace consists of only the 0 vector, we see what happens. Okay. Now let's do a little proof by contradiction. Let's say y of t, let me call this some y1, is c of t phi t comma t0 x naught, Okay. Now, the unobservable subspace contains only of the 0 vector, then there exists at most one initial state which is compatible with the input output pair. Okay. Now, let me see that there is also the same y1 for which there exists another x naught, say x naught tilde, again coming from the C and phi. Okay. So, there is the same y naught which comes from x naught, same y1 which comes from x naught, the same y1 which comes from x naught tilde. So, this implies that 0, I just do the subtraction, C of t phi t comma t0 times x naught minus x naught tilde. Okay, what do I know? That the unobservable subspace consists of only the 0 vector, and therefore, x naught. So, this when it is not equal to 0, right, this would necessarily belong to the unobservable subspace. Okay. So, this is a contradiction here, right. So, what was the claim? That the when the unobservable subspace consists of only the 0 vector. So, the definitions come from here, right. When the unobservable space consists of only the 0 vector, then there exists at most one initial state which is compatible with the input output pair. So, I assume that there are actually two of them, right. So, I just do proof by contradiction. If there are two of these initial states, right, then I just do the subtraction, and I essentially claim here that the 0 is C phi x minus x 0, which essentially means that x minus x 0 would have to belong to the unobservable subspace, which means it is not true, right. And therefore, x naught is necessarily equal to x naught tilde, and therefore, when the system is observable, I can uniquely construct x naught, right. That is what this statement means over here, right. Okay. So, similarly with the unconstructable subspaces. So, what is the definition? So, when I talk of constructibility, I am looking at finding this T1 given the set of measurements between u and y between T naught and T1. Okay. So, the future state of the system xt at xt1 can also be related to the system's input and output. Again, you use the same formulas that we derived earlier. I will not go into the derivation of this. Okay. So, what does the definition say? So, if I have 2 times T1 and T naught, the unconstructible subspace consists of all states for which this holds. Okay. Now, the system is constructible if its unconstructible subspace contains only the 0 vector, right. So, there is only one. So, if its unconstructible subspace has only the 0 vector, similar to the observable thing, right. So, when system was observable, when its observable subspace consisted only of the 0 vector. And of course, these two properties are now very obvious, right, as in the previous case. So, when a particular state x1 is compatible with the input output pair, then x1 plus x2 is also compatible. Okay. And then when the unconstructible subspace consists only the 0 vector, then the x1 is unique, right. Then there exists at most one final state which is compatible with the input output pair, which is compatible with the measurements that we do between this interval, the measurements y and then the inputs u, which are also measurable. So, this was a brief introduction to the characterization of observability and constructibility. So, we will do a very small example before we end for today of what do these things actually look like. So, if I have a system, okay, so let me call this x1 dot is, okay, I will draw a little bigger one. X1 dot is A1 x1 plus B1 u, and then y is C1 x1. Okay, this is one system, and then there is another system here which is x2 dot is a2 x2 plus b2u, y is output here is c2 x2. Okay, and then okay, I'll call this y1, I'll call this y2. Both systems are driven by the same input u. I take both the outputs here, y1 and y2, and together I measure y. Okay, so this is easy. So we have two systems. So I think we'll just write it down. So the overall system will look something like this: x dot, which is x1 dot, x2 dot is a1 0 0 a2 with x plus b1 b2 and u, and y is c1 c2 x1 x2, that is c1 x1 plus c2 x2, that is essentially y1 plus y2. Okay, so y of t, which is the overall output, is given as c1. Again, I use the same definitions of the state transition matrix, the way I compute the solutions and so on. C1, this will be C2 e power a2t x2 naught plus the terms in the integral 0 to t C1 e power a1t minus tau b1 plus C2 e power a2 t minus tau b2 u tau d tau. Okay, when in a special case when a1 a2 are all equal to a, c1 c2 are equal to c. Okay, note that I don't really say anything about the b because that's not really important here. So y of t now takes the form of c e power at x1 naught plus x2 naught plus all the terms in the integral. Okay, so what does this go on to suggest? So the problem of observability was, can I measure just y? I am not measuring this individually, I am just measuring this, and I want to get an estimate of what is x1 naught and x2 naught. So by this expression we can conclude that by only knowing y of t, we cannot distinguish between initial states for which okay. So I cannot really measure x1 naught and x2 naught just from the information given to me. Okay, so what we will do in the next lecture is to find out or to derive conditions by which I can measure observability and constructability, and then we will also derive a nice equivalence between controllability and observability and see that these two are the dual of each other. Okay, so that will be coming up in the next couple of lectures. Thanks for listening.